Hey. Going good. I guess so.
Are we doing an activity in FEA today?
Yep. Mm-hmm. It's our next one, activity, activity number 3.
Maybe like last time where you kind of just let us do it.
Yeah. And so I'll probably spend the first like 30-ish minutes kind of introducing it, and then I'll let you guys work, and I'll go around and help you guys.
And then the homework is due on Monday, right?
Yes. Yep. All right, it's 4 o'clock, so let's go ahead and get started today. Good afternoon, everyone. How's everyone doing today? Good, good. Yeah, we're end of week 5 now, and so we're chugging right along. Okay, and so just a reminder, so next week, next Wednesday is going to be our midterm, and so remember that's going to be a completely in-person midterm. And so I'll send an email reminding you guys of that next week, but please plan to be in the classroom next Wednesday for the midterm exam. Okay. I did post a study guide on the on Canvas as well as a poll, and so those are there to help you guys study. And so at least make sure you check out the poll sometime before Friday, because on Friday I'm going to be recording a review video to kind of help you guys study for the class, right? And so the video I plan for those to be around an hour 15 long, so roughly the same amount of time as the lecture, but it's just for review. And so please vote in the poll. And so sometimes when I put those polls, I get very poor turnout, and so sometimes only like 3 or 4 people answer that. And so when I make the review video, I know those 3 or 4 people will be happy, but I don't know about everyone else. And so those things are they work the best when more people in the class answer them. And so please make sure you go and answer that poll. So your voice will be heard for what I'm going to cover on the review session. Okay. Homework. The next homework is due on Monday, and so that's homework 3. And so I know there was kind of a short turnaround for that one, but homework 3 just consists of short answer problems, and so hopefully it shouldn't take you guys too long to knock out, right? And I will post the solutions for homework 2 as soon as I grade them, and then homework 3 I'll put the solutions for that right after it's due, just so that you guys will have it available for you for study. Okay. Okay. Any questions on anything before we get started? Okay. All right. Okay, and so the plan for today is I have a little bit of the lecture notes on muscle biomechanics to finish up, and then we're going to start talking about joints. Okay. All right, so let's go ahead and pick up where we left off on Monday. Okay. All right, and so the next section in the muscle biomechanics lecture notes is characterizing muscle force generation. All right. And so the idea with this is that we know that muscle are the only force generating tissue that we have in our body. And so how we characterize that force is something that's important for measuring its performance. Okay. And so in particular, the magnitude of the tensile force generated by muscle, it depends on several different factors. And so some factors that it can depend on are things like the speed at which the muscle shortens. And so what you'll see, I'll draw a graph of it on the next page, but the faster that the muscle contracts, the less force that it can support. Right? Okay. The next thing is the length of the muscle when it's stimulated. Right? And so we talked about that in the last couple lectures, right? And so we know that muscles, just like most elastic materials, have elastic properties. And so if you stretch the muscle beforehand, then the elastic properties of the muscle are going to help it kind of pull back. Okay. And then another factor is the period of time since the muscle receives the stimulus. Okay. All right, and we talked about that a bit last time, right? Because we know that your muscles are stimulated by nerve signals, and so the more nerve signals that they receive, right? And so we talked about that volley of signals, right? The more signals that it receives, then the more force that it can generate. Okay? All right. And so particularly, I want to focus a bit more on point number 1, right? Because I think that's the one that we haven't really talked about too much. Okay. And so when a muscle is maximally activated, Or in other words, it reaches a state of tetanus, right? And remember, we talked about that last time, is that's when the muscle can exert its full tension. Okay? When a muscle is maximally activated, the speed at which it contracts depends on the force that's opposing. Okay? Okay. All right, so generally, what you expect is that when you have smaller loads that are opposing your muscle contraction, then you can contract really quickly, right? And so if you're holding just like a pen inside your hand, you can contract that really quickly because it's small. But if you have something like a 20-pound weight, it's going to be a lot slower because it takes, a lot more force to do that. Okay. All right, and so generally there's actually a graph that shows this relationship between velocity and maximum load that the muscle can exert. And I'll show that on the next page. Actually, no, I can fit it here. Let me draw it here. Okay. So we have this graph. Okay. And so on the x-axis here, we have velocity. Okay. And on the y-axis here, we have maximum force generated, or maximum load. Okay. And there's a point in this graph in the middle, so we'll call this zero velocity. Okay. All right. And so for higher velocities, for higher velocity muscle contraction, you can only do that if you're only supporting a small amount of load, right? And so the graph starts kind of below over here. Right? Then as the velocity gets slower and slower, then your muscle can support more and more weight. Okay? And so we kind of have this relationship right here. Okay? And so it reaches a point here at zero velocity. And so at zero velocity, this point right here is called the isometric maximum. Oh, isoparametric maximum, sorry. Remember what isometric means. So isometric basically means you're contracting your muscle, but no motion is taking place, right? And so at that point, you kind of support the maximum load that you can while on that side. Okay? But actually, if you continue on the other side, right? And so if you continue on the other side of velocity, and so if the velocity is negative, then the amount of force that you can generate actually increases further. Okay. And that's a case when you have eccentric muscle contraction, right? So remember we talked about last time about eccentric muscle contraction, where your muscle is contracting, but your limb is moving in the opposite direction that it's contracting, right? And so in those cases, the muscle can actually exert more force than the isoparametric maximum. Okay. And so if I can label this graph, on this side we have eccentric contraction. And on the right side here, we have concentric contraction. Remember, concentric contraction is when you contract your muscle and it goes in that direction at which you're contracting. Eccentric is when your muscle is acting as a brake. Okay? And the main reason we have a higher amount of force being generated in the eccentric side is that as your muscle is being moved in the opposite direction which is contracting, then a lot more of the elastic properties of the muscle are kicking in. And so basically your muscle is extending and stretching out. And so you have elastic kind of internal forces that are helping to kind of assist with that force. Okay. Right. Any questions on any of this? A question. More control is more force generated. I wouldn't say it's more control. I would say it's just it's this force that's generated here. You can think of it as the external load, and so that's the amount of force that the muscle is supporting. Right? And so, think of the y-axis here is, how heavy is the object that you're trying to lift with your muscle, right? And so the way you can interpret this is that the heavier the load, the slower that your muscle can contract. Right. Okay, so let's go ahead and move on. Actually, let me summarize that last point really quick, because it is kind of important. Okay. And so the amount of force that the muscle can exert increases in eccentric contraction. And the reason is because of the elastic properties of the muscle. Okay. And these elastic properties, they're so strong that it can actually enhance the force by about 1.5 to 2 times higher than the isometric maximum. Okay. Right, and so this gives kind of further evidence to, kind of like we talked about, I think maybe a couple lectures ago, where if you want to increase the amount of force that you generate, you want to, kind of stretch it out as much as you can to give it that elastic boost. Okay. All right, and so that's how we can characterize muscular force. Right. So now let's talk about muscular strength. All right. And so, I think this is of interest to, many people besides just, people interested in biomechanics, because people are always trying to measure their muscular strength, right? So you've probably gone into an arm wrestling match with someone before, where you're trying to, push or see how many push-ups you can do, right? And so how much strength your muscles can exert is always going to be a topic of interest. Right? And so the purest way, I would say, the purest way to measure muscular strength is actually to cut it out, attach it to a force meter, and then stimulate it with an impulse, right? And so then you can see, just based, purely scientifically in a very controlled environment, how much force it can generate. Right? Which obviously, is hard to do for human muscle, right? No one wants to cut out their muscle, right? But you can actually do experiments with actually, doing something as simple as going to the supermarket. I'll never forget in graduate school, I had a colleague who was interested in cardiac biomechanics, and so basically measuring how the heart beats. And so he went down and he drove down to the local Asian grocery store, 99 Ranch, and he bought a pig heart that they had on sale there. And he strapped it up to a laboratory setup and he gave it some impulses, and it's starting to beat. I was like, wow, I didn't know you could buy something like that just from 99 Ranch and do a scientific experiment like that. But it's possible. Right? And so this has been done. And so, some scientists have actually done and, gotten muscles from cadavers and stimulated the amount of force that it generates. Okay. And what they measure is that, per cross-sectional area, okay, scientists have found that a very wide range of pressures, right? And so the amount of force a muscle fiber can exert is anywhere between 45 to 420 kilopascals. Which of course is a ginormous range, right? And so it's almost not helpful, but you know, at least we have an upper bound and a lower bound for how much force a muscle can generate, right? And the reason, you know, the reason we have such a large range here is that, you know, not all muscle fibers are the same, right? And so different muscles and different parts of your bodies have different roles to play. And so the amount of force that they can generate when you stimulate them is of course going to be different. But at least, you know, we have an idea of the range of forces that we can get. Okay? And of course, you know, this varies kind of person to person as well. And so kind of the way that normally, you know, we measure muscular force then is something more of an in vivo test. And so what I mean by that is, you know, we take a living person and we give them a test to do in order to see how strong their muscles are. Okay. And so, you know, the amount of force that a muscle can generate, or the amount of strength, usually is measured in terms of how much torque or how much torsion it can produce. Okay. Right, because a muscle is always going to be attached to a joint at some point. And so by measuring how much torque that it can produce around that joint, that's typically how we measure muscular strength. All right, any questions on this? Okay. All right. But when you start thinking about it in terms of this, it gets a little bit complicated because the way that muscle is attached to the joint is different every single time. Right? And so let me go ahead and draw a your typical elbow joint here. Okay? So here we have the humerus, here we have the elbow joint, and then here's the radius and the ulna. Okay, and then our muscle is going to come in kind of like this. And so this person, I guess, is supremely jacked because I drew that muscle extremely big. Okay. But the amount of force that it exerts is going to be in that direction, right? And if we take this joint as kind of the pivot on which it's rotating around, we can compute the torque that this force kind of exerts around that joint. But we know just from mechanics that you know, torque, you know, not only depends on the magnitude of the force that's generated, it also depends on the geometry of the situation too, right? Right. And so of course it depends on the moment arm, and so it depends on the distance between the force and the pivot. Okay. Okay. But it also depends on the direction of the force too, right? Because what you'll see happen a lot in the body, and we'll see this over the next few weeks, is that a lot of muscle forces actually push directly into the joint. Okay. It's a little bit, I kind of drew this figure not that well, but if I draw kind of an extracted figure here, right? And so here, let's say this is the joint. And so let's say that we have a force that pulls like in this direction. Not all of this force is going to go towards rotating or the torque around that joint, right? Because if you break down this force into its components, right? And so let's say that we have a component in the x direction, right? And a component in the y direction, right? The x component of this force, this component is not going to contribute to the torque at all because it's pushing right into the joint, right? And so if you compute the moment arm of that component of the force, it's going to be 0 because it pushes right into it. Right. And so in fact, this parallel, we call this the parallel component of the force. This is only going to contribute to either pushing the bone into the joint or pulling it away from the joint. Okay. Right. And so to actually produce a force, or in order to produce a torque, that muscle force has to be, pretty significant, and that depends on, the angle in which it attaches to the bone. Okay. And so once we start doing some static analysis of certain parts of the body, you might be surprised at how much force the muscles actually have to exert to support, even just the most modest loads, right? Even something as simple as just standing up, right? Even just standing up and maintaining balance, the muscles in your back have to exert, probably hundreds of pounds of force just to keep you from tipping over. Right? And so it's really interesting. And in activities that doesn't seem like you're exerting your body too much, your muscles are actually working pretty hard behind the scenes. And it's mostly just because there's, muscles typically have pretty small moment arms, and so your muscles attach usually pretty close to your joints in most cases. And a lot of your muscles, they're not perpendicular to the bone too. And so because they have a significant parallel portion, not much of the muscle force is actually going towards, producing a torque. Okay. So this is kind of a little sneak preview of kind of where we're going for about the three-ish weeks after the midterm, and we're going to be doing a lot of this, static analysis inside the body where we actually compute, how much force the muscles are exerting. Okay. Any questions on any of this? Okay. All right, and so just to sum it up, right? And so when we characterize the strength of a muscle, there's 3 kind of main factors that are considered. Right? So one, of course, is the amount of tension that it could develop. Right. 2 is the moment arm, and so the distance between the muscle and the corresponding joint. And then 3, the angle of attachment. which determines how much of a parallel component and how much of a perpendicular component that you have to your muscle. And so 2 and 3, you know, we usually don't think about those a lot when we think about strength, right? But also 2 and 3 is not much that you can do. You can't really do much about those. That's just kind of the way you were born and where your muscles attach. But, you know, if you want to increase the strength of your muscles, the only thing you really have power over is just the first one, right? Okay. All right, and so let's talk just a couple more definitions, and then we'll close up this chapter on muscles, right? And so, you know, we're talking a lot about, you know, the amount of force that the muscle can exert, but a lot of times, you know, another factor for muscles to consider is how long can it sustain this force, right? And so another factor is the endurance of a muscle. Okay? So let's go ahead and define muscular endurance. And so muscular endurance refers to the ability for a muscle to exert tension over a long period of time. Okay. Next is muscle fatigue. Right. And so muscle fatigue is an exercise-induced reduction in maximal force capacity in the muscle. Right? And so after you exercise for a while or after you use the muscle quite a bit, you know, naturally the muscle is going to be able to exert less force. Right? Okay. All right, and so generally what we say is that if a muscle will fatigue, the faster a muscle fatigues, the less endurance it has. Okay. Right. One other really interesting phenomenon is the fact that muscle performance actually changes with temperature. And so at elevated temperatures, or if you elevate the temperature of your muscles, you know, higher than its resting state, then you can actually achieve a higher maximum isometric tension. Okay. As well as the maximum shortening velocity. So your muscles will be able to contract faster and, you know, more strongly at elevated temperatures. Right? And so part of the reason for this is that the metabolic processes within your muscle, and so things like your muscle receiving oxygen from the bloodstream, the processes of your cells, generating power from the mitochondria. These processes are enhanced at higher temperatures, right? And so, when people say that, they have to warm up their muscles or they have to, do warm-ups, this is part of the, it's not all of the motivation, but this is part of the motivation is that their muscles just work a little bit better once they're warmed up. Question. So does the increase in blood flow around the muscles contribute to muscle performance as well? Yes. Yeah, absolutely. Yeah. And so the blood is the is the way that your muscles receive all the nutrients and oxygens that it needs to to perform. And so part of the reason, when you exercise, your heart rate goes up. That means that your muscles are demanding a lot more oxygen and a lot more nutrients in order for it to keep up with the demands of the exercise. And so increase in blood flow will also increase your muscle performance. Yeah. Mm-hmm. All right, any questions on this? Okay. All right, and so last thing I want to talk about muscles is common muscle injuries. All right, and so there's a lot of ways that your muscles can get hurt, okay? But thankfully, compared to bones and compared to joints, your muscles are the easiest to heal just because they're so well supplied with blood, right? And so if you do get a muscle injury, it's usually better than than injuring your ligament or injuring your bones, okay? All right, and so probably one of the most common muscle injuries is a strain. And so a strain is basically your muscle is either overstretched or it was torn during an action. Okay. And the way this typically occurs is either from overloading, right? And so you apply too much load onto the muscle. Okay. Or another common way this happens is if your body moves in a very unnatural way very quickly. And so the severity of a strain is, there's a lot of variance in it depending on how much you overloaded it or how bad the motion was, right? And so this can be anywhere from just, very minimal structural damage. Okay. To partial tearing. Okay. To all the way to a complete tear. And so that's probably one of the worst ones that we can. Okay. And so those are the range of severities, right? And so one common place in your body that's subject to strains are your hamstrings. Right. So when your PE teacher asks you if you pull the hammy, he's asking you if you have a hamstring strain. All right. So those are strains. Okay. The next most common muscle injury is a contusion. Right. So otherwise known as a bruise. Right. And so this is, and so contusion will happen when a muscle sustains a large compressive force or an impact. Right? And so what this does is that it basically causes a rupture of some kind of internal blood vessel or in some internal fluid within the muscle. Right? Okay. Right. And so that's why, when you bruise something, oftentimes it's going to turn blue because that's the blood that's kind of leaking out into different parts of your muscles, right? And so, very serious. So most contusions, they kind of heal on their own over time. But very serious contusions can actually cause some permanent damage to the muscle tissues. You write that word again. So the permanent damage is called a calcification. And so what that means is that your muscle fibers will then start to take on a lot of calcium, and that makes your muscles hard and unable to produce tension. And so that's kind of the worst case that can happen. But it's not too common. Most contusions are okay to heal on their own. All right. Any questions on this? Okay. All right. The next one, the next muscle injury are cramps. Right, so probably we've all experienced cramps at in some degree or another. Okay. And so cramps, if you ever had them before, you know that you just start to feel an intense pain and intense knotting in your muscles, right? And if you look up the current research on cramps, their cause right now is actually still largely unknown. There's been some research into linking things into the amount of hydration that you have in your body, right? And so people always tell you that when you have a cramp, you should drink a lot of water just to replenish the fluids and electrolytes in your body. Okay? But a lot of that is not super conclusive yet, right? And so by and large, cramps, their cause is still mostly unknown. Okay? But but the symptoms of a cramp is just kind of intense muscle spasms or muscle pain. Okay? Right, and so some possible causes are electrolyte imbalance, deficiencies in certain, important vitamins and minerals, and dehydration. Okay, but it's still very much an area of research. All right, and so the last, this is not really an injury, but I would say it's kind of more of a feeling that you get. It's called delayed onset muscle soreness. Right. And so this refers to the pain and swelling in your muscles that you experience after you've done some vigorous exercise. Right. And so usually this occurs when you have exercised for the first time in a while. And so this is the soreness that you feel in your muscles, right? And so usually this happens about 24 to 72 hours after strenuous exercise. Okay. I will never forget this. So in high school, I played soccer in high school. And coming in as a freshman, we actually went to Seal Beach down to have like a summer practice. And we ran a couple miles on the beach. And if you've ever run on sand, you know that you have to do a lot to kind of your legs kind of have to work a lot to dig yourself out of the sand with each step. And so I remember waking up the next day and my calves were just on fire and I couldn't do anything. But we still had practice the next day, and so that was not a fun time. Question. Midfield. Oh, I played defender mostly. Yeah, I played in front of the goalkeeper. Yeah. Mm-hmm. All right. Any final questions on muscles before we move on to talk about joints? Okay. All right. And so let's start talking about joints. So that took a little bit longer than I thought, but it's okay. We do have some time. I do have some time built into the semester. Okay. All right. So let's talk about human joints. Okay. And another name that you'll see for joints are articulations. Okay. But most people, at least in casual conversation, we call them joints. But sometimes people call them articulations because they're basically the point where, or the locations where two bones are articulating with each other, or they're meeting. Okay. All right. And so we've covered bones and we've covered muscles, but joints are kind of the other big kind of structural component to your body. Okay. And your joints are really important because they basically govern the type and direction of motion of your body segments. Okay. Right. And what kinds of motion that's allowed there is mostly determined by the geometry of the joints, right? Okay. Right. And so, we just got done talking about muscles, right? And so muscles, when they pull on your bones, right? The types of motions that can actually occur, your joints are the ones that determine that. It's not really the muscles, right? Because there's a lot of and I would say at almost every joint in your body, your muscle will want to pull your body segment one way, but the joint kind of prevents certain kinds of motion just based purely on the geometry. Okay. And so, if you're working on designing things like prosthetic devices, or you're working on designing, protective sports equipment, your knowledge of joints is essential. Okay. Okay. Another reason we're interested in the joints is because your joints are probably the parts of your body that have the most moving parts, right? And if you've done any kind of mechanical design on the machine, you know that, and anywhere that you have moving parts, that's where complications tend to occur, right? And so for the body, these complications result in injuries. And so a lot of the injuries that people sustain, things like sprains and things like that, a lot of them happen at the joints. Okay. And so two important characteristics for the joints that will more clearly define later on and as we go through these notes are joint stability and joint flexibility. And these two are actually opposing forces. So generally your more stable joints are going to be the ones that are less flexible, right? And generally the joints that are more flexible are less stable and more subject to injury. Although there are exceptions, and it's all kind of based on the geometry. And so as an example, let me draw or attempt to draw one of the most stable joints in your body, which is your hip joint. Okay. Right. And so your hip joint basically consists of of the head of your femur, of your thigh bone, inserting into your pelvic bone. Right? And so it looks something like this. Right? And so your femur kind of comes up like this. You have this kind of roundish ball. Okay? And then your pelvic bone kind of goes around it like this. So this is your femur. And this is your pelvic bone. Or at least very poor drawings of this. Right? And so, the most, I would say the most defining characteristic of your hip joint is the fact that you have this very large kind of spherical head of the femur, right? And a very deep socket on which it rests, right? And so this is the classical kind of ball and socket joint that you have in your body, right? And it's as close to like a real mechanical ball and socket that you would normally have for a device or a machine, right? And so you have a very kind of large kind of ball and then a very deep socket. Okay? And so because there's so much contact in this joint, and so there's basically that entire femoral head is kind of locked into that that socket, that gives this joint just supreme flexibility, right? Or supreme stability. I'm sorry. And so it's you'll see that hip dislocations where this femoral head actually pops out. Those are extremely uncommon because of just how stable this joint is. Right? All right. Any questions on this so far? Okay. All right. So let's start by kind of defining all the different types of joints in your body because there's a lot of them. Right? I know we kind of introduced this a little bit in our initial lecture on anatomy. But there are more joints than kind of what I originally mentioned, right? Because before what I just mentioned was strictly the joints that move. But there's a lot of joints in your body where there's actually either no movement or very little movement. Okay? Remember, joints are just defined as the places where your bones kind of meet up together. And so let's talk about joint architecture. Okay. And so, the first, batch of the first kind of classification that we'll make is based on the amount of movement that's allowed at the joints. Okay. All right, and so the first type of joint that we'll go over are the most stable ones, okay? And these are the immovable joints. And so these joints have a lot of what's called fibrous kind of tissue around it, okay? Because these joints are not meant to move. And so what this tissue does, because it's so thick and so fibrous, it's very good at absorbing or attenuating the forces that it that acts on it. Okay. Okay. But just like its name, it permits very little movement, either very little movement or no movement at all. Right. And the fact that we have no movement there is a combination of, you often don't have muscles that can pull, in the direction of those joints, right? And so there's no muscle there that can actually, cause any motion. But also just, the fact that it's so densely packed with tissue that with kind of cartilage tissue that it just doesn't allow any movement just from that. Okay. So some examples of the movable joint in your body. And so the joints between your skull plates are immovable joints. Right. Remember, we talked about the skull, not being all one bone. It's actually a lot of different plates that are kind of meshed together. And so in between those skull plates are immovable joints, right? And so your skull is not supposed to move around, but it has to all stay in one place. Okay? And another location where you might not expect is between the fibula and the tibia. And both of these are your shin bones. And so you have two bones in your lower leg and your shin, and so in between them, there's no movement, really no movement between them. So that's why you have an immovable joint there. All right. And so that's the first kind of joint. The second type of joint that we have are slightly movable joints. Very descriptive naming convention that they have. And so these joints consist of mostly cartilage, and they can allow some very slight movement. Okay. But they also share a lot of the properties for immovable joints in that they're also very good at absorbing force. Okay. Right. And so some examples of slightly movable joints would be the joints in between your different vertebrate bones or between your spine bones. Right? Another case of a slightly movable joint is your sternum, right? Or the middle of your ribs. That's another slightly movable joint. Okay. All right. Any questions on this so far? Okay. All right, and so those are the two the two joints that I'd say we don't really talk too much about just because there's no motion there. But the next category of joints are the freely movable ones, and this breaks down further into the types of motion that they allow. Right. So the next type we have are the freely movable joints. What's that? Let's see. You know, girl. Oh yeah, yeah. I mean, yeah. Anytime you use gym equipment, you have to use it properly. You know, otherwise you're gonna injure yourself. Hope she's okay. Okay. And so the third category of joints that we'll go over are the freely movable ones. Okay. And so in these joints, you know, because they're designed for movement, the bones that make up this joint are coated with what's called synovial fluid and a synovial membrane. Okay? Right. Right. And so if you think about, you know, mechanical parts that are designed to move past each other, right? And so you think of things like gears in an engine, right? Or you think of like a robotic arm, right? One of the most important things that you need to consider in those situations is proper lubrication, right? And so whenever you have, you know, mechanical parts moving past each other, rubbing each other, right? You need to make sure that you cut down on the amount of friction force as much as possible in order to properly preserve the part, right? And so it's the same thing for the body. And so the way that the body lubricates their movable joints is they use synovial fluid. Okay? And so this synovial fluid basically acts like lubrication. Okay. Right, and so, you know, because these joints are so varied in the body, we can break down their classification further into the types of motions that they allow. Right? And so some of this is going to be a little bit of review, but, you know, I'm going to repeat some of it just for the sake of completeness. Right? Right, and so the first type of movable joint that we have is a gliding joint, right? And so for gliding joints, the bone surfaces at these joints are mostly flat, right? And they only allow, you know, one translational degree of freedom, right? And so they basically only allow gliding. Okay. And if you remember, you know, from our our initial lecture, right, one example of a gliding joint would be, you know, the joints in your hands and your feet, right? So the tarsals and the carpals. Right. And so another type of joint is a hinge, right? And so in these joints, the articulating bones form a hinge, okay? where usually one surface is concave and the other is convex. Okay. Okay. And as we learned before, hinge joints, they only allow one rotational degree of freedom. Okay. Right, and so these joints can mostly only rotate around one axis, right? And so, common examples of this would be like your knee joint, your elbow joint, right? And so those only can rotate basically around a hinge. Okay, any questions on this so far? All right, and so the next two, we didn't really talk about it before, but their motion is kind of in between a hinge joint and a ball and socket joint, which is the last one that we'll cover. Okay. And I'll go ahead and just for now, I'll group these two into the same one because they're pretty similar. Okay. And so these are called condyloid joints and saddle joints. They're very similar to each other. It's just that, one is a little bit bigger than the other one. One allows slightly more motion. Okay. All right. And so, to kind of describe it in words, like one, both bone surfaces that come to these joints, they kind of look like a horse saddle. One of those horse saddles being convex and the other one being concave, just so that they can kind of mate together, right? And so, what these allow for is a much greater range of motion than hinge joints, but not as much as a ball and socket. And so, the way that it's described here is that it allows for flexion, extension, abduction, adduction, and circumduction. Circumduction basically just means that you're rotating around the joint surface itself. All right. And so one example of a condyloid joint or a saddle joint would be like your thumb, right? And so the way your thumb kind of attaches to your hand, you can do all different kinds of motions with your thumb. Okay. Right. And according to most scientists, the thumb is basically our opposable thumbs is basically how we conquered the world, because not that many animals can actually grab and pick things up with the ease that we do. Okay. Any questions on any of this? Okay. All right. And so the last joint, it's one that we've covered before, is the ball and socket joint. And so we drew a picture of this on the very first page of this joint lecture notes, right? And so the ball and socket joint basically looks like one articulating surface looks like a ball, and the other one is the socket in which the ball fits into. Okay. Right, and so ball and socket joints allow for the greatest degree of motion. Right, and so of course, the hip joint is a ball and socket joint, and then the other one is your shoulder. That's the other combo. Okay. All right. And so, as we start to study, the different parts of the body, it's going to be really important to know, what type of motion that's normally allowed at the joint. Okay. Because it's important to know, when you're, studying a particular joint, if you know what motions that it can allow, that can help you do things like assess injury or other things like that. Okay. And so, for example, if we take the knee joint, we know that the knee joint is a pretty classical hinge joint. Okay. And so if this is the front of the knee, right? And so this is the front of the knee with the patellas out here. Okay. We know that the knee can only act as a hinge, and so it can only flex and extend going back into the page. If something were to strike it like this, right? And so we have a large force, okay, and such that the knee kind of does this, right? And so it bends like that. And so remember, you're looking at the front of the knee, right? We know that the knee is not supposed to do this because the joint that the knee is a part of is not designed for this motion, right? And so most often, if you have some kind of unnatural motion at the joints like this, either caused by external trauma or some external force, then it's likely that you're going to have an injury that occurs. Okay. And so you can use this information to design, something like a knee brace, right? And so let's say that you work for like a sports equipment company, right? And so what you can do is, so knowing that you want to prevent this types of motion, you can design a knee brace, right? That's going to go over the knee, okay? And maybe your knee brace is going to have supporting structures like right here and right here, right on the sides. And so this is a pretty common design for like a knee brace for people that are worried about these kinds of injuries, right? And so if you have stiff plates are here, right? Then if something impacts your knee from the side, then those stiff plates are going to absorb that impact and prevent the knee from bending in the unnatural way. Right? And so just knowledge of the joint motion can help you design a device like this. Okay? And actually, last year there was a senior design group that I talked to briefly, and they were designing a knee brace, specifically for something like this, right? I didn't get to see how they finished, but from some of the preliminary designs that I saw, they were considering some designs like that. Okay, any questions on this? Okay. All right, so we're almost out of time, but let me just introduce the idea of joint stability, and then we'll pick this up on Monday. Okay. All right. And so, when we talk about joint stability, we talk about a joint's ability to resist dislocation. Because one of the common injuries that you'll see at a joint is a dislocation, right? And so the bone will pop out of the joint and kind of not be able to move in there anymore, right? And so some of the factors that affect joint stability is just how much contact area there is between the articulating bone, right? And so generally, for bones that have a large amount of contact area in the joints, those are going to be pretty stable, right? Like your hip joint is really stable just because there's so much contact there. But if we look at the other ball and socket joint in your body, the shoulder, that one's actually one of the most unstable joints in your body just because there's actually very little contact in your shoulder, right? And so that's why you always see people dislocate their shoulder when they're either playing sports or they're working out in the field. Okay. All right. Any final questions on this before we wrap it up for today, for this week? Okay. All right. So thank you guys. Thank you guys for tuning in today. I know it's a busy time, so I appreciate you guys coming out to the lectures. And so have a great weekend, everyone. Remember, our midterm is next Wednesday, and so we all need to be here for that. Okay. And so if I don't see you on Monday, I'll see you for sure in person on Wednesday. Right. And so have a great weekend, everyone, and I'll see you next week. Oh, that I know. Oh, 7.
Yeah. Stay away. I'll have to go online and retake those notes for sure. My handwriting gets really messy.
It's that time of the semester. I know it's
it's
tough.
on Wednesdays, so like I like to work out here because like they have like nice bodybuilding machines and stuff. But the thing is that I don't really like their free weight equipment. So